We are in Chapter 3, Additional Applications of the Derivative. 3.1 is increasing and decreasing functions and relative extrema. So first thing that we have says a function is increasing if it goes up from left to right, and decreasing if it goes down from left to right. So an increasing function, if we sketch a few coordinate planes on here, is going to be a function that is increasing from left to right. And so this would be our increasing function. And a decreasing function would be if it's falling from left to right or decreasing. And again, you read a graph just like how you read a book from left to right. The example right below says determine the intervals on which the function of the graph below is increasing and where it's decreasing. So again, remember that for intervals we need to use our x values. And also we need to determine where it's increasing and where it's decreasing. So this first part of our graph is rising from left to right, so it is increasing. The second one is falling, so that would be decreasing. The next part increases. The next part decreases. And that last one is increasing. And you'll notice that these are switching at these, what they're called as maximums and minimums of our graph. And so the graph also, if you want to, you can add some arrow tips. Sometimes graphs don't have those on them, but they are, meaning that they go on forever if they don't have a solid point. And so where is it increasing? So using those x values, it's increasing forever to the left, so it's going from negative infinity until this maximum up here, which we'll say is at negative 2.5. We don't exactly know where it is, but we are going to estimate it the best we can. And then the next interval that we have where it's increasing is going from 0 for our x value to 2. I'm going to put u here for union, so those are both increasing. And then the last one that we have, it looks like it's at about 3.5 on to infinity. Likewise, looking at our decreasing units, we have from negative 2.5, and so it went from negative 2.5 all the way to 0 for our x value, union, and then the last little one that we have here that is decreasing, I'll highlight it, is going from 2 to 3.5. So we'll say from 2 to 3.5. Also note that I'm using parentheses on all these and not brackets, and the reason why is that technically at maximums and minimums it's neither increasing nor decreasing, it's constant there. And so if a function changes from increasing to decreasing or decreasing to increasing, it's changing at those maximums and minimum values. So these are our intervals from where it's going from increasing and also for it decreasing. So right below this, it says, let f of x be a function divided on the interval from a to b, and let x1 and x2 be two numbers on the interval. Then an increasing interval will have a positive slope, which means that your y values, or f of x2 is greater than f of x1 for x2 greater than x1. So it'd be increasing. The next bullet point says decreasing intervals are where we have a negative slope, which means f of x2 is less than f of x1 for x2 greater than x1. So this would be where it's falling from left to right. And then the third one is a horizontal interval. Will have 0 slope, which means that your y values are going to be the same. So it's going to have a horizontal slope. And so next thing that we have is what's called critical numbers or critical values. And this is going to be for a function f are those numbers c in the domain of f for which our derivative is equal to 0 or where the derivative does not exist. Critical numbers are the maximums and minimums of f of x and the x-intercepts of our derivative. So definitely something to know here. We have critical points, which is an ordered pair, and remember an ordered pair just is x comma y, whose x-coordinate is the critical number and the y-coordinate is f of c. So plugging that back into the original function that we have. The graph right below is an example of a function that we could have, and so you can see that where f is decreasing, our derivative would be less than 0. Where f is increasing, our derivative is greater than 0. And then where the derivative is equal to 0, it's either where we have constant or where we have these maximums and minimums. So the first test that we have here is called our increasing and decreasing test. And this says let f of x be a differentiable function on the open interval from a to b. If our derivative f prime of x is greater than 0 for all the x values in that interval, so our derivative is positive, then f of x is increasing on that interval. Likewise, if our derivative is less than 0 or negative, then f of x is decreasing on that interval. So applying the increasing and decreasing test using derivatives, the first thing that you need to do is find your critical numbers, which is going to be checking to see where our derivative is equal to 0, which is going to be where our maximums and minimums would occur, or where it is undefined. Then use the critical numbers to find open intervals. 3 is going to be choose a value in each of those intervals and substitute it into the derivative. And if the derivative is greater than 0, it's increasing. If it's less than 0, it's decreasing. And if it equals 0, then it's a constant interval that we would have. There's no change. We have an example right below. This is find the intervals on which f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and where it's decreasing. So the first thing to note is that our function is a polynomial and the domain for this function would be all real numbers. So I'll put down domain is going to be all real numbers, which again, because this is a polynomial. And so in order to find out where we have intervals of increasing and decreasing on our function, first thing we need to do is find our critical numbers. And to find our critical numbers, we need to first take a derivative. So f prime of x, and taking the derivative of our function that was given using the power rule, we're going to have 12x to the third minus 12x squared minus 24x. And we need to set this equal to 0. And so I'm going to go ahead and say equal to 0. And to solve this, I'm going to go ahead and factor out my GCF, which in this problem is 12 and an x. And so we're left over with x squared minus x minus 2 equals 0. And we can continue and factor this. And so this is a factor to x minus 2 and x plus 1 using that guess and check method. And again, checking to make sure that you factor that correctly. And then from here we have 3 factors. I'm going to set each of these equal to 0. So we have 12x equals 0, x minus 2 equals 0, and x plus 1 equals 0. I get x equals 0, x equals 2, and x equals negative 1. And so these are my critical values or critical numbers. I'm going to label this CV for critical values. So critical numbers or critical values also occur where the derivative is undefined, but since our derivative up above is just a polynomial, our derivative is defined everywhere, so it's never undefined. So step 2 says use the critical numbers to find open intervals. And so since our domain was all real numbers, I'm going to go ahead and draw a number line here and put some arrow tips on the end. So it's all real numbers. If it is a limited domain, make sure you only look at that limited domain. Our critical values are -1, 0, and 2. And we need to test something in each of these intervals. So something that's less than -1, you can select anything in that interval. If you want to select -1000, -2, -5, anything, but we need to test them. And we're going to substitute them into our derivative. So I need to find f prime of -2. And then something in between -1 and 0, I'm going to select -0.5. so negative 0.5. Something between 0 and 2, I'm going to select 1. And something larger than 2, I'll just select 3. And so what we need to do is substitute these into our derivative, which we found, and I'll go ahead and underline that or box it. And so if you substitute in negative 2, you will arrive at, if you work that out, a negative answer. And so that means that this interval right here would be negative. And if you wanted to, you can look at just the signs. The numerical value does not matter. It's just if it's positive or if it's negative. And so you can substitute it in actually easier to the factored form of our derivative. And if you did this, you'll notice that that first term's negative. The second term's negative, because negative 2 minus 2 would be negative. And then negative 2 plus 1 is also negative. So a negative times a negative times a negative is also a negative. So using that same logic, I'm going to substitute in negative 0.5 into my factored form of my derivative. And so the first term's negative, the second term's negative, and the last one would be positive. So negative times a negative still is positive. And then the next one, I'm going to substitute in 1. So first factor is positive, second one would be negative, and the third one would be positive. So this would be negative. And then substituting in 3, I have positive, positive, and positive. So multiplying all positive numbers would still be positive. Again, some students like to actually substitute in the numbers and get a numerical value with that sign. The numerical value does not matter. We're just looking at the sign. So make sure that you do what you feel comfortable with, and definitely ask if you have any questions. So it was asking for the intervals, which again, remember for intervals, we're always using our x values. And those x values that you're going to be using are going to be these critical values that we had, which was negative 1, 0, and 2. And so the first thing is, let's write down where it is increasing. And so increasing would be where it's positive. So these are where it's increasing. And so it's going to be going from negative 1 to 0. And from 2 to infinity. And then it's going to be decreasing when it's negative. So it's decreasing from negative infinity to negative 1, and also from 0 to 2. So these would be our answers that we have. Right below this, we have relative maximums and minimums. Let C be a number in the domain of function f. Then f of c is a relative or a local maximum if f of x is less than c for all x in that interval from a to b, and a relative minimum or local minimum if f of x is greater than c for all x in that interval a to b. It says if a function f has a relative extrema, maximum or minimum, at c, then c is a critical number, or c is an endpoint of the domain. Relative extrema, a relative maximum or relative minimum of the function f, and a polynomial of degree n can have at most n minus 1 relative extremas. And so a lot of the homework problems will ask to find the relative extrema, and that just means you need to find both the relative maximums and relative minimums of your function. And so there is a picture there, and you can see that relative maximums and relative minimums and where they occur, they could also occur at endpoints. So they can also occur at endpoints, which is important to note. And so they either occur at the critical values or at endpoints. So the example on the next page says find the location and the values of all relative extrema for the function f of x of the graph given below. So we want relative extremas. So that means all of those maximums and minimums. And so looking at our graph, you'll notice that my left endpoint goes on forever since I have an arrow tip there. And so there would be no relative max or min there. The next one that we have, since it's a top point, this would be our relative max. Then the next one, since it's a low point, this would be a relative min. We have a relative max. And just labeling these. And again, your relative max would be like the top if you think of it as like a mountain peak. And then this last one that we have is going to be, since it's at a bottom and decreasing to get to that, we're going to call this one a relative min. So it wants to know the location, the values of the relative extremas, and we're going to go ahead and write these as ordered pairs the best that we can. And let's go ahead and do relative maximums or local maximums first. And so the first one that we have is at -5,1. And then the next relative maximum we have is at 0,3. And then the last one, we have one more relative max, and that is occurring at 4,1. And then we have a relative min. And our relative min, the first one that we have over here on the left, is occurring at -3, -2. Our next relative min is at 2,0. And then the next relative min that we have is that endpoint, which is at 6, -2. And so these are the location of those relative extrema that we have. So we can algebraically determine where the relative extremas are located by using the first derivative test. And so the first derivative test is listed right below. That says, let C be a critical number or critical value of a continuous function f of x. Then, if the derivative changes from positive to negative at C, then f is going to have a relative maximum at C. So if you think about this, going from a positive value, so positive slope, to a negative slope, you would have a relative maximum up there. So if it goes from positive to negative, and then likewise it says if our derivative changes from negative to positive, so going from a negative slope to a positive slope, so negative slope to positive slope, it's going to have a relative minimum at C. The third one says if a derivative has no change, so it stays from positive to positive or negative to negative, then no relative max or min will occur at C. A visual approach to the first derivative test is given below. Let C be a critical number. And so for the first one that we have right here, if it goes from increasing to decreasing, that's going to be a maximum. And so this would be a relative max at C. The next one goes from decreasing to increasing, and so we'd have a relative min at C. And then the next one, the two down below, it goes from positive to positive, or increasing to increasing. So this means no, we would not have any relative max and mins. And then likewise, decreasing to decreasing, same thing. So none there. It's not changing, it's staying constant. So the next thing we have is steps to use the first derivative test to analyze critical numbers given f of x. So our first thing here would be to find all critical numbers C. Then using the number line, break the domain into open intervals using the critical numbers. Determine where f is increasing, decreasing on each interval. And if there is a change from increasing to decreasing, there's a relative max. And a change from decreasing to increasing, there's a relative min. And so we have an example at the top of the next page that says find the location and values of all relative extrema for the function f prime of x with the graph below. So first of all, notice that we're not given a function, we're given the derivative. And so this is a graph of the derivative. And so our critical values, which normally are going to be our maximum and minimums, but since we're talking about a derivative here, this is going to be our critical values are where our function, the derivative of it, is going to be equal to 0, or these are our x-intercepts. And so our critical values are going to be our x-intercepts. I'm going to go ahead and put points at all my x-intercepts. And so your function is going to be increasing where the derivative is positive. It is positive above the x-axis where any of those y values are positive. So all of this is positive or increasing. Likewise, it is going to be decreasing where your graph of the derivative is below the x-axis. So I'm going to go ahead and label that with the little negative and decreasing. And so it wants to know where our function has any relative extrema. And so if you notice, the first critical value that we have is at -4. And at -4, so at -4, it goes from positive slope to negative slope. And so that means that we would have a relative max at x equals -4. We don't have the original function, so I'm unable to find what the y values are at those. And then we have our next one, which is at -2. And at -2, it goes from decreasing to increasing. And so we have a relative min at x equals -2. The last critical value that we have is at x equals 3. And if you notice, it goes from positive to positive. And so this means that there is no relative extrema, or no. So I'll put down none. The next example says find all the x values of the points where the function defined as follows has any relative extrema. Classify them as relative max or mins. And so the first part that we have here is f of x equals x squared plus 8x plus 5. And so for this, in order to find these relative extremas, we first need to take a derivative. So we're going to find f prime of x. And so our derivative is going to be 2x plus 8. And we're going to set this equal to 0. And then solving this, we get 2x equals -8, or x is equal to -4. And so this is going to be one of our critical values, or critical numbers. Also note that our derivative is never undefined because it's a polynomial. And also the domain of our original function, since it is also a polynomial, is all real numbers. And so the next thing we're going to do is draw our number line and put on our critical values. And since our domain is all real numbers, I'm going to put arrow tips symbolizing that it goes on forever. The only critical value that we have is -4. So selecting a value to test in each of these intervals, I'm going to go ahead and substitute those into my derivative. Something smaller than -4, I'm going to go ahead and substitute in -5. Something larger than -4, whenever given the opportunity, I select 0. But you can select anything in those intervals. So substituting in -5, we have -5 times 2 plus 8, which would work out to be a negative value. So that means that this would be negative or decreasing. And then substituting in 0, I just get 8, which is positive. So this would be increasing. And so it's decreasing on the first part and then increasing on the second. And so we're going to have a relative min at x equals -4. And again, it only wanted those x values, but if you did want to find the y value, or if the question is asking for that, or if you have to graph this, you would need to substitute in -4 into your function. And so you would have to have f of -4, and so you'd have -4 squared plus 8 times -4 plus 5. And then working this out, you should get -11. And so our value occurs at x equals -4. However, that point would be -4 comma -11. The next one right below this is B, and I'm going to circle that one, and we will look at that one together in class. The next example says, the revenue derived from the sale of a new kind of motorized skateboard T weeks after it's introduced is given by r of t equals 63t minus t squared over t squared plus 63 for t between 0 and $63 million. When does maximum revenue occur? What is the maximum revenue? So the first thing is to note is that we're dealing with millions of dollars here, and it's asking about maximizing our revenue and what that maximum revenue is. So since we have a revenue function that is given, to find that max revenue, we need to first take a derivative, set it equal to 0, and then determine what the critical values are, and then seeing if they're where that maximum would occur. So the first thing to note is that we are given an interval between 0 and 63, so it's not dealing with all real numbers. And so keeping that in mind for t. And so first, our revenue derivative of that function, we need to use the quotient rule for this. And so we have the bottom times the derivative of the top, which is 63 minus 2t, minus the top, which is 63t minus t squared, times the derivative of the bottom, which would be 2t, all over the denominator squared. So t squared plus 63 quantity squared. From here, I'm going to simplify this by multiplying out my first two terms and then subtracting and distributing that other set. And so from here, we're going to end up with 63t squared minus 2t cubed plus 3,969 minus 126t, and that would be foiling out that first part. And then minus, and so we have to distribute our 2t and then also distribute our negative. So we're going to end up with minus 126t squared plus 2t cubed, all over, and the denominator still is t squared plus 63 squared, equals, and then so from here we can simplify, and if you notice your t cubed terms would reduce out. So combining our terms, we have t squared terms, we end up with negative 63t squared, and then we have negative 126t, and then plus 3,969 all over t squared plus 63 quantity squared. From here, we're able to factor out a negative 63, and we get t squared minus 2t minus 63 all over t squared plus 63 squared. And then we're actually able to factor that numerator. So this is going to equal negative 63. And using guess and check to factor this, what multiplies to negative 63 would be 9 and 7, with one of those being negative. The larger term does need to be positive since it is a positive 2 in the middle. And so we have t plus 9 and t minus 7 all over that same denominator of t squared plus 63 quantity squared. So to find our critical values, we're going to set this equal to 0. And then from here, we have negative 63, t plus 9, t minus 7 equals 0. And we get that by multiplying both sides by that denominator. From here, the negative 63 you can divide out or just ignore it. But we get t plus 9 equals 0 and t minus 7 equals 0. Or t equals negative 9 and t equals positive 7. So t is our time. And so we're dealing with t weeks, and so t is not able to be negative, and so the only critical value that we have that we are interested in is t is equal to 7. And so our time that we have is also given to us as between 0 and 63. And so when I draw my number line, I'm going to have it start at 0 and it's going to go to 63. And the only critical value that we have is 7. And so we need to find a value in each of these intervals to see if it's increasing or decreasing or positive or negative. And substituting in a value between 0 and 7 to our derivative of our revenue function, I'm going to select 1 since that's an easy value to sub in. And then something larger than 7, I'll go ahead and substitute in 10. Again, anything between 7 and 63 you're able to use. So substituting in 1 into my derivative, you can see that your derivative is always going to be positive in the denominator with the factored form, and looking at that like we've done before. And then you'll notice that we have a negative 63. Substituting in 1, we get a positive term for that next t plus 9. And then 1 minus 7 would be negative, and a negative times a negative would be positive. So this is an increasing function between 0 and 7 in that interval. And then the next interval that we have from 7 to 63, I'm going to substitute in 10. So we have negative 63 times a positive value, 10 plus 9. And then 10 minus 7 is also positive. So we have just negative times positive or negative. So this is also decreasing. Again, if you feel more comfortable substituting in those values into that and actually working them out and getting a numerical value, you definitely can. And so since it's going from increasing to decreasing, that means that we have a max. So we have maximize our revenue at t equals 7, and our units again up above our weeks. So we maximize our revenue at 7 weeks. And to find our max revenue, we will need to substitute in 7 into our original revenue function, not the derivative, that's the rate. And so substituting in 7 into the given function up above, the typed one, we're going to have 63 times 7 minus 7 squared all over 7 squared plus 63. And working this out, we get 3.5. And our units for revenue are given in millions of dollars. So this is going to be $3.5 million.